Modern high-performance computing clusters are built for massive parallelization, taking millions of individual data tasks and executing them simultaneously across tens of thousands of processors. But when researchers attempt to simulate subatomic physical reality, like lattice quantum chromodynamics or nuclear effective field theories, they run into complex sign problems where the resulting matrices become highly oscillatory. To simulate a single grid with a volume of 128 cubed by 512, a state-of-the-art classical cluster requires 1,500 exaflop hours. This illustrates why classical systems stall. Adding particles expands the quantum simulation's state space exponentially, scaling memory at big O of 2 to the n. Splitting the calculation across nodes fails. The math quickly exceeds every individual processor's RAM. Classical computing has reached a physical ceiling for simulating quantum mechanics. The immediate mathematical answer lies in quantum hardware. The current generation operates in the noisy intermediate-scale quantum, or NISQ era. These processors handle exponential state spaces natively because their qubits behave like the subatomic systems they are simulating. However, NISQ devices suffer from high error rates and short coherence times. The qubits lose their state before a lengthy end-to-end algorithmic simulation can finish. The path forward requires linking classical infrastructure with quantum hardware to form a hybrid architecture. This integration relies on isolating quantum-ready primitives. In this cluster schematic, a complete algorithmic workflow is fracture, and only the mathematically native tasks are routed directly to the quantum processing unit. By treating the QPU as a highly specialized accelerator node, the system leverages classical stability for overall management, while offloading the specific exponential math that chokes standard processors. This flowchart visualizes a standard Hamiltonian simulation, broken into 3 stages. We begin with initialization. Simulating the interactions of a spin lattice, like the Heisenberg model, requires preparing a highly entangled initial ground state. The classical approach relies on exact diagonalization. This requires the system to construct and store a full, dense matrix representing every possible state permutation. This data visualization plots classical memory usage against the number of simulated spins. At just 14 spins, the matrix requires storing almost 7 gigabytes of data. Beyond this, the memory requirement spikes exponentially. Quantum computation approaches this same problem using a variational quantum eigensolver, or VQE. Instead of a massive matrix, VQE uses parameterized quantum circuits to establish the entangled state in hardware. Thus, the quantum gate count scales polynomially. Notice how the linear track of quantum circuit depth entirely ignores the exponential curve of the classical memory wall. Once the state is initialized, the simulation moves to the evolution stage. Here, the system calculates how the quantum state changes over time according to Schrödinger's equation, dynamically updating the physical properties. Classical supercomputers typically use Krylov subspace methods to approximate this time evolution operator without constructing the full matrix. Yet the computational cost remains heavily tied to system size. This line graph plots the classical execution time for simulating the Ising model. As the system scales past 12 to 14 spins, the matrix vector multiplications force the runtime into a steep exponential climb. The quantum primitive designed to bypass this bottleneck is trotterization. Trotterization breaks down a complex Hamiltonian operator into a sequential chain of simpler components. Each component translates into a native gate operation that the QPU executes directly. Plotted against the classical runtime, the circuit depth for 10 trotter steps grows at a slow, predictable linear rate. This efficiency requires a strict trade-off. Trotterization introduces minor approximation errors into the simulation in exchange for drastically shorter circuit depths. In the NISQ era, minimizing circuit depth is a physical requirement. If the gate sequence takes too long, qubits will decohere and the calculation fails. Trotterization strategically sacrifices exact mathematical precision to guarantee operability on noisy quantum hardware, making it an ideal primitive for offloading. After the system evolves, it reaches the final stage, measurement. The goal here is to extract observable physical properties from the evolved state, such as energy levels or magnetic alignment, to calculate expectation values. To calculate these values classically, the processor must generate dense probability distributions, demanding the full state vector be held in memory. Quantum hardware extracts this data using statistical sampling. The device prepares and measures the system in repeated independent intervals called shots, each lasting only microseconds. Because the qubits physically represent the probabilities, these repeated shots directly yield the expectation values without ever reconstructing or storing a state vector. This scatter plot tracks the mean measured expectation values on a logarithmic scale. As the shot count on the x-axis increases, the scattered results converge tightly onto the exact classical value, and the error bars shrink. Ramping up the number of independent measurements cleanly drives down the standard deviation and refines the precision of the output. The measurement phase transitions from a classical memory constraint into a highly parallelizable exercise in rapid statistical sampling. Zooming out, we observe how these hardware components interact within a massive computing infrastructure. The workflow begins on the classical HPC nodes. Here, classical processors use tensor networks to generate a mean field approximation, producing an initial mathematical guess of the system state. This diagram traces the handoff. The classical node routes the initial guess to the QPU, which executes VQE state preparation and trotterized evolution. The QPU then returns the raw sampled data. The classical processor applies Bayesian inference to filter the output, stabilizing the final result. The success of this architecture relies on the classical supercomputer operating as a robust, error-correcting supervisor for a highly capable, fragile quantum engine. To maintain this continuous feedback loop, the infrastructure must overcome severe network latency. Moving high-dimensional data between CPUs, GPUs, and QPUs requires ultra-low latency remote direct memory access, or RDMA fabrics. RDMA allows one node to write directly into the memory of another without interrupting either operating system kernel. This protocol enables the microsecond communication speeds required to correct quantum errors in real time. The hardware industry is actively working toward fully fault-tolerant quantum computers, capable of executing complex simulations without heavy classical oversight. Until that hardware matures, identifying quantum-ready primitives and orchestrating them through high-speed hybrid networks remains the only viable blueprint for